An Introduction to the Theory of Automorphic Functions by Lester Ford. Chapter 1, Linear Transformations. Section 3, Conformal Transformations. Let P be a point in a plane, and let C1 and C2 be two curves issuing from P. Let theta be the angle between the curves, i.e. the angle between their tangents at P. For convenience, we shall consider the angle positive if, in passing from a point on C1 to a point on C2 through the region of the included angle, the motion is counterclockwise around P. Now, let a transformation of the plane be made such that P, C1, C2 are transformed into a point P' and two curves C1' and C2' issuing therefrom. The transformed angle, theta prime, will be that angle between C1' and C2', which includes the transforms of the points within the original angle theta. It is positive if in passing from C1' to C2' through the included angle, the motion is counterclockwise around P'. The cases with which we shall chiefly be concerned are those in which theta prime is equal to plus or minus theta. Definition: a transformation preserving the magnitude of angles is called a conformal transformation. It is directly or inversely conformal according as the sign of the angle is preserved or changed. It is a theorem in the element of the theory of functions that a transformation of the complex plane z' equal f of z, where f of z is any analytic function of z, preserves both the magnitude and signs of the angles, except at the points where f of z has singularities. Laying aside the 2 points z equal infinity and z equal to minus d divided by c, the latter of which gives z prime equal infinity, since we have not defined the angle between lines meeting at infinity, we can state for reference the following. Theorem 6. The linear transformation is directly conformal. It is a theorem of the theory of functions whose proof is beyond the scope of this tract that the most general directly conformal transformation of the z-plane is of the form z' equals f of z, where f of z is an analytic function of z. In general, the correspondence of the points of the z-plane and those of the z' plane is not one-to-one. For example, z' equal the square root of z gives two values for z' for each value of z. Z' equals the sine of z gives infinitely many values of z for each value of z'. The question naturally arises whether the linear transformation is the most general one possessing the quality of uniqueness mentioned in Theorem 2. This is in fact the case. For let z' equal to f of z be the most general function yielding a one-to-one transformation. Let z equal to q be the point for which z' is equal to infinity. Z' then has a pole at q and nowhere else. The function can be written in the form z' is equal to am divided by the quantity z minus q to the mth power plus am minus 1 divided by z minus q to the m minus 1 plus plus a1 divided by the quantity z minus q plus a0, where m is the order of the pole. Clearing the fractions, we get an equation of the mth order in z. To each value of z', there are m values of z, hence m must equal 1. Therefore, z' equal to a1 divided by the quantity z minus q plus a0 is equal to a0z plus a1 minus a0q, all divided by the quantity z minus q, which is of the form equation 1. We have then established the following. Theorem 7. The most general one-to-one directly conformal transformation of the plane into itself is a linear transformation. An Introduction to the Theory of Automorphic Functions. This book was written by Lester R. Ford, M.A., Harvard, lecturer in mathematics in the University of Edinburgh. It was published in 1915 by G. Bell & Sons Limited, London, and is now in the public domain. It is read by Jim Renholt with programming and illustrations by Jim Renholt in 2019. Thank you for listening.